Hi everyone, I'm back with another video on chapter 10. This one covers section 10.3 of guided notes. That would be page 15. And in this video, I'm going to show you how to find the sample size for z-test. Because in any testing procedure, it is very important that we know what would be a good sample size to start with. So suppose you want to test H naught mu equal to mu naught versus HA mu greater than mu naught, and if you specify alpha and beta, where beta is evaluated at mu equal to mu A greater than mu naught, some value of mu, say. So then further adjustment of test involves two remaining quantities, right? N and the point at which the rejection region begins, and the point at which the rejection region begins. So that would be, those are the four things, remember, that you can play around with to get an optimal test. So basically we have alpha and beta are known and n and k are unknown. So we can solve them simultaneously to find n. We can write alpha and beta as probabilities involving n and k. So alpha is probability that y bar is greater than k given mu is equal to mu naught, which is probability y bar minus mu naught over sigma by square root of n is greater than k minus mu naught over sigma by square root of n given mu is equal to mu naught, which is probability of z greater than z alpha, and beta is probability that y bar is less than k because you fail to reject, given mu is equal to mu a, whatever the value it takes in the alternate space, which is probability of y bar minus mu a over sigma by square root of n less than equal to k minus mu a over sigma by square root of n, which is probability of z less than equal to minus z alpha. So from these two equations, so you have two equations, right? One and equation 2. You can solve them simultaneously to get the value of n. So k minus mu naught over sigma by square root of n is equal to z alpha, and k minus mu a over sigma by square root of n is negative z alpha, beta, sorry, it should be beta. Let me just erase it. So now we have these two equations. We can solve both of them simultaneously for k. So both for k. So from here k is, so from this one k is z alpha plus times sigma over square root of n plus mu naught, and from here k is mu a minus z beta sigma over square root of n. So if we equate both of them, that means z alpha times sigma over square root of n plus mu naught is equal to mu a minus z beta times sigma over square root of n. Now you can do some algebra, and that would give you square root of n is equal to z alpha plus z beta over mu a minus mu naught sigma which implies that n is equal to z alpha plus z beta over mu a minus mu naught square sigma square. So there is an example on page 16. Let's do that. So in example 10.3.1 on page 16, it's a solved example, but I'm just going to quickly go over it. Suppose so if you think of, we have one example where the vice president was making some claim about mean contact number of contacts a customer service agent makes or something like that. So in that, h naught was mu equal to 15, ha was mu equal to 16. If you fix your alpha and beta to be 0.05, so basically you want the level of significance to be 5%, and you want your power to be 1 minus 5, that is 95% power, and you wanted to find what should be an optimal sample size for that. Assume sigma square, so they are giving they will provide, because usually sigma square is unknown, so they'll give you some value. So in this problem they're telling you sigma square is 9. Sometimes they give you range, and then you can use if range is given, then you can use sigma as range over 4, range divided by 4. It's a very crude estimate of sigma. So just plug everything back in the formula: z beta, z alpha, z beta square, mu a minus mu naught whole square sigma square. Z alpha is 1.645 plus z beta is also same because they are same. Alpha beta both are 0.05. Mu in the alternate space is 16, in the null space it is 15, and sigma squared is 9, which gives you 97.4, always rounded up to the next integer, so 98. So 98 observations should be used to meet the requirement of alpha and beta to be 0.05 for the vice president's test.